Okay, thanks guys. Okay, so today we have two talks. Thanks for coming to the new GCSP seminar. And we're gonna have a talk from Nicolas Garavito, who is a finishing grad student at University of Arizona working with Gertina Besla, who just gave a talk to the colloquium last week. So this will be a nice follow-up to her talk. And he's gonna talk to us today about the dynamics of the Milky Way in the presence of the SMC and LMC. So just a reminder with the talk format, each speaker has about 20 minutes plus 5 to 10 minutes for questions. We're asking, feel free to ask a question during the talk, but if you can wait till the end just so we can adhere to the time limit, feel free to put it in the chat or and ask it at the end. So thanks, I'll let Nico just start.
Thank you. Can you allow me to share my screen? I think I cannot do it. Right.
Isn't that letting you share the screen?
Yeah, not yet.
It should let you share.
No.
No,
it says.
All right, nope, there you go. Yeah.
Yeah.
Should work now.
Got it. Yeah. Yeah. So hopefully everyone can hear me and see my slides. Yeah. So today I'm going to talk about. I changed the title a little bit, but near field cosmology with the Large Magellanic Cloud. This is work that I have done with Gertina Besla at the University of Arizona during my PhD. And thank you, all of you, for having me here today. It's a real pleasure to be here. And yeah, let's get started. So roughly, I'm going to talk about near field cosmology in the Milky Way. So to put the topic here, the idea is that we have the stellar halo of the Milky Way, which is this extended structure, which is really faint, but has a lot of important information about how the galaxy has been assembled over time. And so you can see a lot of substructure here, which are remnants of this process of accretion in the galaxy. And if you want to learn more about this, I really recommend reading Rohan's native paper about the nice work with the HS3 survey. But another application of the stellar halo is that if you have velocities and position of the stars, you can map the enclosed mass of the Milky Way. And at these scales, the majority of the mass is dark matter. So you can map the underlying dark matter halo using the stellar halo. And this is important right now. This is crucial because, as illustrated in this picture, like SDSS already covered part of the stellar halo. You can see the inner parts. This is the 20 inner KPC region of the galaxy. But with current data and with more data that like LSST, we are going to reveal all the structure of the stellar halo, so up to 200 KPC or so. And importantly, we will have what is called the multidimensional view, which is we have photometry, spectroscopy, proper motions. So with all of this data, we can really constrain what is the dark matter distribution and the assembly of the galaxy in detail. So this is the very nice picture that Gaia provides us. And what I would like to highlight in my talk is that the Large Magellanic Cloud that you see here is also an opportunity to even learn more about dark matter and how the galaxy has assembled. So an overview, a brief overview of the LMC and the interaction with the Milky Way. The LMC is currently on its first infall into the Milky Way. So this is more or less the orbit. It just passed its pericenter, first pericenter approach. And it's right now at 50 kpc, so it's inside the stellar halo and the dark matter halo of the Milky Way, and this is going to be important. And roughly, the mass of the LMC is 10 to 20% that of the Milky Way. So it's an important contribution of mass, and it's perturbing the Milky Way, and this is exciting. So when I say we want to recover the assembly history of the galaxy and map the dark matter halo, there are many ways to do this, which are listed here. I'm not going to go into detail, but for example, yeah, you can get the mass profile, the shape of the halo. So there are many things that people have done. But what I would like to highlight is that in the recent 2 or 3 years, it has been shown that the LMC has effect on all of these methods. So it's important to take into account for the LMC. What I'm going to focus today in my talk is what is the LMC doing to the dark matter halo shape of the Milky Way, and what is its implication for the planes of satellites that I'm going to talk about later. Okay, so why we care about shapes of dark matter halos? And so we have a model, a very successful model that says that galaxies grow through this accretion of other galaxies. And in that accretion, like the accretion is not isotropic, it comes through filaments. And what this causes is that the shape of the halo, of the host halo, is not going to be spherical, it's going to be triaxial. So basically the shape of the halo have information about this accretion history. So often, the best halo that we can map is the Milky Way. So we would like to compare how is the shape of the Milky Way compared with the simulation, with the theory, right? But as I have said, the Milky Way is in presence of this ongoing merger with the LMC. So before we compare with uh, the theory, we really need to know what is the LMC doing to the shape of the Milky Way. Okay, so it's common that a way to measure halo shapes is by fitting 3D ellipsoids. As I said, the halo shape is not spherical. So often we fit like these prolate or oblate shapes to the halo. And depending on the accretion history of the halo, like the shape of a halo can change as a function of radius, or it could be very complicated. But this is just the methodology, so we are going to come back to this later. Okay, so if we want to study what is the LMC doing, so what I did is I performed 8 n-body simulations, which are shown. This is a movie of one of these. These simulations, I have 4 different LMC mass models. As I said, we don't have tight constraints on what is the mass of the LMC. So I have 4 LMC mass models, 2 Milky Way models, which just differ by the kinematic structure of the halo, but they have the same mass. And what is important about the simulation is that they reproduce the present day position and velocity to the observed one within 2 sigma. So we think that we constrain very well the orbit of the LMC. An important aspect of that I want to highlight of the ongoing interaction is that maybe you can see a cat here. I don't have a cat in my simulation, but the cat is illustrating something important, and is that as the LMC comes, the cusp or the inner regions of the Milky Way is moving due to the gravitational interaction with the LMC. This is not happening. I mean, the halo is not rigid, so you expect that the inner parts are moving with respect to the outer parts of the halo. So I'm going to come back to this, what I call the cusp motion of the inner region. This is going to have important consequences that we're going to look at later, but keep that in mind. So let's review what is going on. So on the left, you see the density contrast, the density of the halo. Yeah, these are contours. And on the right, you see the density contrast of dark matter particles. You see that as the LMC comes, so this is a movie as a function of time. You see that there are overdensities that has been created. So the most important one is this one, which is the dark matter wake. This is how the halo is responding to the passage of the LMC, right? And this is what causes dynamical friction. This is what makes the LMC lose angular momentum and energy, and eventually is going to decay in the inner regions. I would say that detecting this huge overdensity, the dark matter wake, is important because it will be the first detection of dark matter in a non-equilibrium wave. It's going to, as you can see, it's changing in time very fast. And in this regime, there are evidence that different dark matter models will predict a different morphology of this dark matter wave. So that would be very important. And I hope you stay tuned because there are good results coming by the HS3 team at Harvard with Charlie Conroy, Rohan, Anna. So stay tuned for that. And yeah, so I'm going to talk about the shape. So I already mentioned what is going on with the wake, which is here. This is the LMC. You can see the disk of the galaxy for references. And then we have this huge overdensity region, like in the north, which is basically what the remnant of that inner motion of the galaxy with respect to the outer parts of the galaxy. This is what we call the collective response. So this is what is going in the halo. just if you just study or take into account the particles from the Milky Way. But the LMC is there also there, right? So there are three things that affect the shape of the Milky Way halo, which is the presence of the LMC itself, the particles that belong to the LMC, so the dark matter particles that now belong to the Milky Way, and the wake and the halo response that I showed earlier, right? So this is the density in this figure. I'm showing the density of these three components combined. So the LMC is here, the Milky Way is in the inner part, and then you can see that even if you start with a spherical halo, like I did in my simulations, you get very distorted shapes, right? But we can say, okay, let's remove the LMC. When we measure the shape of the Milky Way halo, we can remove the LMC. So this is what we get. So now I remove the LMC, but still I have the debris from the LMC. And by the way, this debris is roughly 50% of the initial mass of the LMC at the beginning, before the LMC enters. So it's a lot of mass, and it will be also very important to detect that dark matter debris. It will be an additional proof of dark matter. And even though that you ignore the LMC, the bond particles, you see that the shape of the halo is very, it's very distorted. And then we can say, okay, let's remove the debris, and we get with what we have before, right? Like this elongated shape that in this region, this is where the dark matter wake exists. Okay, so now the question is, and for completeness, this is what the LMC shape look like. This is the debris and the wake, and this is the wake, right? So when you subtract the monopole term, the spherical term here, this is what you get. So how we measure this? I already mentioned that there is this method that we have ellipsoids that we fit, but in these distorted shapes, maybe that's not accurate enough. So a way to do this is using basis function expansions, which is basically, imagine that you start with a given halo. In this case, this halo is very axisymmetric, but it's just for this example. And then you want to know what is the shape of this halo. You can do that by saying, okay, I will assume a first term that I know, like let's say a spherical term that is well known. This could be an NFW profile or a Helmholtz profile. And then I want to put perturbations on top of this profile that I already know very well. Once I do that, then I will have an expansion of all of these perturbations. And then when the series converge, then I will say, okay, I reproduce the halo that I wanted to do. And then you can do this for even more distorted shapes. And all the information of these terms are in this coefficient, which tell you what is the amplitude of these perturbations. And the nice thing is that you can get all of this information only with the positions of the particles in your simulation, in the simulation. So it's very efficient to compute. So, okay, so I did this for the Milky Way halo, both with the debris and without the debris. And this is what I get. So on the x-axis, this is the order of the expansion. So 0 is the monopole term, 1 is the dipole term, and so on. And on the y-axis, this is the amplitude of each term. The dashed lines is for the simulation with the LMC debris, and the solid line is without the debris. What you get is that the spherical term is of course the most important, but also you have contribution from the dipole, quadrupole, and so on. The dipole, for example, is mainly due because we have this huge collective response here, right? So that induces a dipole kind of shape. Now, when you compare this with what you get, for example, when you measure a cosmological halo with a similar mass of the Milky Way, but that doesn't have an LMC. So this was work by Zhao at the CfA. So I made a halo with that kind of ellipticity, and then I compute what is the basis function expansions, and this is what we get, right? So you see that, yeah, they also have a very that halo also have a very spherical component, but it also have more components, right? Because it's not only spherical. Interestingly, like because you are using this ellipsoid method, this method doesn't have any non-axisymmetric terms. So it doesn't have a dipole or an octopole. So we are already losing information if we want to measure the Milky Way halo with that method. We couldn't have this non-axisymmetric term. But also more importantly, like you start seeing that at these high orders now, the amplitude of the terms is comparable to what the Milky Way and to what with the LMC is doing in the Milky Way halo. So this is saying that in a cosmological halo, you have many accretion events that create these distorted shapes, but the LMC, just with one pericenter, can induce these distorted shapes that could mimic the level of triaxiality that we are measuring in cosmological halos. So this is create a challenge if we want to compare the LMC and the Milky Way halo with the theory. We really need to characterize what is the shape, the distortions caused by the LMC. Okay, so to summarize this part of the talk, so the shape of the Milky Way halo has information of the wake that I showed the movie and the cosp motion. And so if we want to measure the Milky Way halo shape, we really need to account for the interaction of the LMC. People have just recently started to do this. And in a recent paper by Vasiliev, you can see how to include the LMC in order to measure the shape of the Milky Way. Axisymmetric models don't account for all the halo shape response. So we need to think about how to really quantify this. And we are proposing using basis function expansion. And the presence of the LMC really complicates effort to place the Milky Way in a cosmological context using halo shape measurements. So we need to really think about how to do that comparison carefully. Okay, now I want to change gears a little bit. I'm going to talk about the Milky Way planes of satellites. And so what's going on is that the Milky Way have more satellite galaxies, and roughly 60 now. And some of them, 11 of them, seems to be co-rotating in a thin plane. So in this picture, I'm showing the disk of the galaxy here, and each of these dots is a satellite galaxy of the Milky Way. The arrows show the velocity. So you see that in this face-on view, most of the satellites are rotating in this direction. And if you see edge-on, they lie like in a very thin plane. This is very uncommon. Like it's like why this is happening, and these people have treated this as a problem for sometimes for the cosmological model. Like this is not very common in other galaxies in the simulations, right? So what's going on? Another way to illustrate this is if you plot the orbital pole. So this is the direction of the angular momentum in galactic coordinates. You get this map. This is the orbital poles map. And basically, because they are rotating, the satellites are rotating in a disk, you get that the direction of the angular momentum is almost the same. So they are in this plot, they're like kind of clustered. So you see that most of the satellites have the orbital pole in this region. It's very interesting that the LMC is kind of in the middle of that circle of orbital poles. So motivated by this, I look into the simulations, and then I say, okay, let's first look at the simulation in isolation. So this is the Milky Way in isolation. The color bar tells you the number of, like, the density of orbital poles in that simulation, and you see that it's homogeneous because it's on Porter, and that's what you expect. We shouldn't expect any preferential direction. Now, when we look at the simulation that have the LMC, that the halo is responding, but not using the LMC particles, just the Milky Way particles, we get this. There is an S shape that is being induced by the LMC. Oh, that's the time?
Okay. Sorry, you got a few minutes.
Okay, I'm about to finish. Thanks. So you see that this S shape here, and this is induced when you have a displacement. Do you remember the cos displacement at the beginning? So this displacement causes this alignment of orbital poles, and the orbital poles are very aligned with the one of the LMC. So this is very curious. The tails of this shape is from particles that are in the outer parts of the halo. But if you look between 50 and 200 kpc, the overdensity of orbital poles is around the LMC. Now, if you look at the simulation and you say, let's look what are the orbital poles of particles that are in the same location of the satellite galaxies, you get the blue dots in the Milky Way in isolation. So you don't see any clustering. But when you do the same exercise in the Milky Way with the LMC simulation, you immediately see that those regions get clustered in both these and this. This is like particles, satellites that are counter-rotating. So this is very promising. And okay, to summarize, not well, to finish, I'm going to use also the method of basis function expansions to model the time-dependent potential of the Milky Way and the LMC, so we can also integrate orbits efficiently, having all the dynamical information of the simulations in a few coefficients. And we expect to release this at the end of the year or early next year. Okay, so finally, to my conclusions. Modeling the dark matter halo response to a massive LMC on the first infall is critical to test cold dark matter models and recover the assembly history of the galaxy with all the sky surveys. The LMC induces a dark matter wake that should be observable and a potential testbed for the nature of dark matter. The LMC also induces the reflex motion that results in a strong dipole in the kinematics of Helios stars that should be observable. The LMC induces a non-symmetric dark matter distribution in the Milky Way dark matter halo, and that is not oblate, prolate, or triaxial. And I'm going to present these models, time-dependent models of the interaction of the Milky Way and the LMC that we can use to integrate orbits. And finally, the existence of a plane of satellites around the Milky Way seems to be a natural explanation of this inner cosp motion induced by the LMC. So, thank you very much for your attention, and let me know if you have questions.
Great, thank you. Do we have any questions? Yes, Anna.
Hi, Nico. Thanks for the great talk. I had a question about the contributions of different multipoles to the total combined field of the both Milky Way and the debris. So it looked like that the was this axisymmetric terms or like the even numbered L's are contribute more than the odd numbered L. So I was wondering whether there's a physical intuition behind this result.
Yeah, so yeah, we are also curious about that, and yeah, thanks for the questions, Anna. And so we think that so the debris kind of make everything more axisymmetric. That we, and I mean, it's like I think it's by just the geometry of the merger with the LMC. Like without the debris, things are very axisymmetric. Like the wake and the collective, like the collective response is what really makes like the odd terms stronger. So I guess that when you have the debris, which is not aligned with the collective response, like could be like in another direction, it makes things, it induces mostly like even terms. But yeah, I think that's.
Oh, that's interesting. Okay, so it's really, it depends on the orbital alignment between, I guess, the Milky Way and the LMC's orbit.
Yeah.
Okay, thanks.
Yeah, thank you.
Rohan?
Lovely work, Nico. My question was, it had to do with the plane of satellites plots that you showed. So there's clustering around the center, but in the Milky Way satellites, do we also see clustering around the other region that you highlighted as where you would expect some clustering, like on the far right?
Yeah, like in the like in these regions.
Yeah, that's right.
Yeah, yeah. So yeah, so for the Milky Way, we observe some satellites that are counter-rotating. They are in the plane, but counter-rotating, and we also see like when we do this exercise, we also see that just by the motion of the cosmos, we also get some satellites that will be counter-rotating. It's because it's like a geometrical issue. You will get yeah, things that seems to be co-rotating and seems to be counter-rotating. So it could also be explained by in this scenario.
Okay, got it. Thank you.
Any more questions? We have enough time for one or two more. Oh, okay, Jesse.
Yeah, thanks for the talk. I wanted to ask you about measuring the actual wake. So right now you're assuming a sort of smooth halo model where you have a collective response, but thanks to Naidu's work, we now know that there's a ton of substructure that have Korean structures. So how do you measure a collective response of individual substructures as opposed to like a smooth halo?
Yeah, thanks for the question. So yeah, we don't expect the stellar halo to be smooth, but we think that this is a large scale perturbation that should be like on top of all the substructure. So and the same for the wake. Like it's like, yeah, we really need to do a better job in the models to take into account substructure to really quantify how these two things get. But we think that this should be observable because it's like a global response that should be on top of all of the other on the substructure. So if you have like large like surveys that cover a large region of the sky, then it would be easier to see, I think.
Gotcha, thanks.
Great, thanks. Well, let's thank Nico again for this great talk, and I will let Sirio introduce our next speaker. Sirio?
Yes, I'm not introducing the next speaker. I don't know who is.
I don't know who is either. I can introduce.
I was contacted by Jason Eastman, I think.
Yeah, is he not in the talk right now? I don't know. Well, I'm happy to introduce you. Well, our next speaker is Lily Zhao. She's finishing her PhD at Yale, correct?
Mm-hmm.
Yeah. And sorry, may I ask who have you been working with?
Deborah Fisher.
Great. Yeah. So Lily will tell us all about a new spectrograph. Yeah. Sorry, Jason should have been here to introduce you.
No, it's fine. I feel like the introductions always spoil a lot of my talk anyway, so this is almost better.
Oh, good. Okay. Well, I will let you begin, and
Let me see.
yeah, you should be able to share.
Can everyone see my talk?
Mm-hmm.
Great, thanks. So like Anna said, my name is Lily. I'm working currently at Yale University in Deborah Fisher's group on EXPRES, the extreme precision spectrograph. So EXPRES is a spectrograph that we designed, built, and commissioned in-house at Yale, designed to bring radio velocities to this era of extreme precision, and also to target finding Earth-like planets. Sorry. So as a quick review, right, radio velocity is the technique where you find planets by measuring the movement of a host star around the common center of mass between the host star and the planet itself. And so we can see that because the starlight from the sun, the host star will be Doppler shifted, and we can measure that Doppler shift and use it to find planets. So far, RV discoveries have been pretty successful so far. And you can see that the first planet was discovered 51 Peg famously by RVs. And ever since then, the detection limit, which is shown by this line here with year, has been going down and down and down until right around this 1 meter per Earth mass mark here. And this is the level of 10 centimeters per second, which is the RV precision we would need if we wanted to discover an Earth-like planet. So a planet the size of Earth orbiting around a star the size of the sun at a distance of 1 AU. And though we had been increasing over the years, we really stalled right before we hit this like 1 Earth mass limit. And so expressed in the work that I've been doing as a graduate student is really trying to push this limit down so that we can finally start finding Earth mass planets. It's just that achieving this 10 centimeter precision is pretty hard, and it really requires innovation at all different levels. And so when we look at a star, we want to be looking at that star with an instrument that's stable enough that when we get our raw data from it, we know that data doesn't have any effects from the instrument varying, the different temperature changes, things like that. All the variations are from the star itself. But when we have this raw data, we also need a new data pipeline that extracts this raw data well enough that it can account for some of the discrepancies or things in the instrument that we couldn't correct for instrumentally or through engineering, and that all of the effects in the spectra are actual effects that we see in the raw data and no weird computational effects and things like that. And then once we have the spectra, we need to model the data in different ways so that we can get RV shifts from the spectra that are from the star and the star alone, and even better from a planet rather than any features on the star itself. And so in this talk, I'm going to go through each of these 3 steps, give a sort of like a description of what EXPRES has done to address each of these 3 topics, and then give a sort of benchmark of how EXPRES is currently doing. And so I'll start with instrument stability. EXPRES is installed at the 4.3 meter Lowell Discovery Telescope near Flagstaff, Arizona. One of our favorite things about this telescope is that it has this instrument cube that all the instruments are hooked up to. And so the TO can literally press a button and within seconds, a different instrument will be on sky. And what this allows us to do is observe for a lot of half or even quarter nights throughout the year, rather than having to have only full nights every so often. Instead, we'll have 3 to 4 quarter nights per week. And this really allows us to build up the long time baseline of observations that are needed to find short period planets, for example, and really get the coverage to characterize a system using radial velocities alone. EXPRES is in a shell spectrograph because this is typically what people do in order to achieve higher resolution, because it spreads out the features a lot more. And so here's kind of just the cartoon of how a shell spectrograph works. The light enters here through an entrance slit. It hits a concave mirror, which then causes the light to leave the mirror in parallel lines rather than from a focal point as before. And then it hits at a shell grating where it gets separated into the different wavelengths of light. A culminating lens after that lines up all the wavelengths of light along with each other, and then it goes through a huge prism, which then separates the light not only in the X or wavelength direction, but in what we call the cross dispersion direction. So that separates the light in both X and Y. So here's a picture of EXPRES itself. EXPRES is environmentally stabilized. So she's pictured here in her vacuum chamber. And this is the optical bench. Both the optical bench is actually made out of invar, which is a particularly thermally inert material. The optical bench is vibrationally isolated from the vacuum chamber, which controls the pressure and passively controls the temperature of the instrument. And the vacuum chamber is vibrationally isolated from the floor of the spectrograph room, which is itself vibrationally isolated from the rest of the building. And so we poured an independent concrete slab to serve as the floor of the spectrograph room, so that when the telescope rotates around on the 2nd floor, those vibrations don't come through and carry into our instrument. EXPRES was designed with a high resolution, and so it averages around 137,000, and it's an optical spectrograph, so its wavelength is between 390 and 780 nanometers. And we finished commissioning in about February of 2019. And so if you look at the cartoon from before, we can kind of match up the parts to the EXPRES spectrograph. We have the fiber input here, so that's where the entrance slit, where the light enters. It hits our main collimator, which is a concave mirror that causes the light to come out in parallel arcs. It hits the shell grating, which was the price of my childhood home, before it bounces through a few optical paths just to fold the light, goes through a transfer collimator, which lines up all the lights, and goes through these cross dispersers, the size of my head, to finally hit our detector back here. A few of my favorite things about EXPRES is that actually before the light even enters the spectrograph, we have this whole front end module on the telescope, including a fiber mirror that makes sure the starlight is hitting the fiber entrance in the same way all the time. And so it slightly moves the fiber mirror as we look at a star to make sure that the light is entering at the same angle. And this fiber mirror actually has a bare fiber, so like a piece of glass the width of a human hair in it, so that the light hits the fiber directly with no occluding optics in between. Our camera barrel has no less than 8 optical elements in it. And so we have all these different lenses here to make sure that the light passes through regardless of wavelength in the same way. And the line spread function, or the way that the light spreads out on the detector due to these optics, changes very little. And if it does, very slowly throughout our detector. And so that data right next to each other on the detector look very similar to each other. And lastly, we have this huge detector that uses new technology from STA to stamp down all the pixels at the same time. And so before, where you'd have different blocks of pixels that might be slightly off against each other, this detector is done in one huge stamp. And so we don't have these pixel position non-uniform stamp non-uniformities that we have to worry about. And when you put all of this stuff together, what you get is an image that looks like this. So this is a raw image of 51 peg taken by the EXPRES spectrograph, where each pixel has been colored by the wavelength that corresponds to that pixel. And so I do mostly show this picture to flex a little bit, but it also shows some important things that will be relevant later on. For example, since it's in a shell spectrograph, you can see that the data appears on these bands or as shell orders across the detector. And so this was the separation in the Y direction I was talking about before. And each of these orders gives like an independent measure of the RV or data within an order and have to be treated separately to a certain extent. The dark lines you can see across are the actual spectral absorption lines from the star. And you'll notice that they're quite vertical, which was done with design, done by an extreme amount of design, honestly, because that means that the wavelength for a row of pixels is the same up and down. And if it weren't, it would make defining what wavelength each pixel is a much harder task. To figure out these wavelengths, what we do is we use calibration sources, so lines that get projected onto this detector with known wavelengths. So here you can see a cutout of the two different types of calibration lamps we have. A thorium-argon lamp, which is just a thorium-argon lamp, and so the emission that arises from the thorium-argon compound show up on these shell orders, and we know the wavelengths of these different lamps. But we also got this fancy new laser frequency comb from Menlo Systems, and it shows this much denser set of lines that cover our detector instead. It's both much more stable than the thorium-argon lines, so we know the wavelengths of each of these lines with much more confidence. And it also informs, gives us much more information, because here where we have gaps between the lines, these are densely sampled. And you can see here that they show up every like 5 to 6 pixels. Another benefit of the laser frequency comb is the calibration light from the laser frequency comb goes from the instrument to our spectrograph, right to our detector into our extraction pipeline. And so what we can do is we can take a series of laser frequency comb exposures right after each other, and then measure the shift between consecutive LFC exposures, which will give us a sense of how stable our instrument and just our instrument is doing. We don't have to worry about anything from this telescope or the star. And so when we do that with EXPRES, we find that there's a scatter with an RMS of about 3.84 centimeters per second from this data set. And from a few others we've taken, we find that the instrument calibration stability of EXPRES is 3 to 7 centimeters per second, which, since it's under 10 centimeters per second, I'd say is doing pretty well. So this is a measure of the instrument stability of EXPRES alone. But from this raw data, we still have to put it through a data pipeline to get spectra that we can use out of it. And since I'm a bit of a narcissist, I will be talking mostly about what I work on, which is the wavelength calibration. So the process of assigning each of these pixels the color that corresponds to it. And if you think about it, since we're trying to measure the shift in wavelength and assign that as an RV shift, you better be sure that each pixel has the wavelength you think it does. Otherwise, it could be mistaken for a completely random or, God forbid, like a red noise contribution that will throw off your RVs. So the question of wavelength calibration has to be done in regards to two things. You have to figure out the wavelength with respect to pixel, which means when you have this nice line of LFCs, you know the wavelengths of each of the lines, but you have to interpolate that information somehow onto the pixels in between each of the calibration lines. And once you do that for all the pixels, you also have to interpolate this information with respect to time. Since EXPRES doesn't use a simultaneous fiber, we tend to take like 3 calibration exposures, some science exposures, and then 3 more. And so we need to take the information from the calibration exposures and map it onto the science exposures in between, so we then know what all the wavelengths of these pixels are. So classically, wavelength calibration is done with polynomials and nothing but polynomials. So here I have plotted the position of all of our calibration lines. This dense region is where we have LFC lines that are right on top of each other. And here you can see the much more sparsely sampled thorium-argon lines. So they're plotted with respect to the position on the detector in the x-axis, the absolute order or number of those bands, which can fill in for the y-axis, and they're colored by the known wavelength of those lines. So first, with respect to pixel, what you would do is you would fit this function to a 2D polynomial in terms of x and m, which is our fill-in for y, in terms of the wavelength, so z on the z-axis. And then what you would do is you would take the coefficient of each of these terms in the 2D polynomial, you would plot that with respect to time, and then fit that curve to another polynomial. So you would take the coefficients of a polynomial, fit it to another polynomial, and then evaluate that polynomial at the time you want to construct a polynomial to describe your function, right? Which is altogether too many polynomials, especially for a device that might not necessarily fit the function of a polynomial. And so as an inaugural predoctoral fellow at the Center for Computational Astrophysics last year, I worked with Professor Haag and Dr. Megan Bedell to create a new way of doing this wavelength calibration task. So we call it Excalibur, and it's a non-parametric hierarchical model for precise wavelength calibration. The non-parametric part, now is the time to move to something non-parametric, so something that doesn't depend on a polynomial, because we have these denser line sources, these LFCs, that give us more information. This plot shows a little bit differently now. The line center is still on the x-axis, but the residual, so if we predicted wavelengths for known calibration lines, how far is our prediction from the known wavelength of that line? So measure how good the prediction is. For different types of predictions, you'll see that here are the thorium-argon lines as pink circles, and the LFC lines are as these black vertical lines. And so if we use a polynomial to predict wavelengths, either using just the thorium-argon lines or just the LFC lines, you'll see them in blue and green. And if we use a non-parametric model, like a cubic spline trained on the thorium-argon lines, you get these huge deviations when we are between two large thorium-argon lines. But if we zoom in, if we use a non-parametric model trained on the LFC lines instead, we get the closest match and the best prediction of the wavelength solutions. And furthermore, the polynomial fits using either thorium-argon or LFC have roughly the same shape, even if the offset is a bit different. So you're not really getting anything out of your LFC by fitting it to a polynomial. And the LFC, not the thorium-argon, is good enough to constrain a non-parametric model and allow the flexibility it needs to fit the wavelength solution better. So now that we have denser line sources, it's really the time for us to move to a non-parametric framework for wavelength calibration. As for the hierarchical part, this comes from the idea that now that we have these ultra-stabilized instruments, every calibration image you take during a period of stability has something to say about every other calibration image you take. So fitting each exposure independently to a polynomial no longer makes sense. And so this is kind of shown in this plot where, again, on the x-axis is the pixel position of the line for just one order. And on the y-axis is exposure number, so a rough metric of time, right? Like where the LFCs next to each other were taken next to each other or close enough in time. And you can see that each LFC line shows up in mostly the same place, right? You have these vertical lines down the figure, but there is some shift that's slow or slow drift that could be traced by the LFC lines. In black here are lines that were just missing from an exposure, either because the LFC malfunctioned or the extraction went bad, something like that. And so if we were treating each exposure independently, these black lines would be information that was just lost to us. But looking at this plot, right, you can say, oh, well, the exposure right before the line was here, and right after the line was here. And so we can kind of guess where that line should be. And so by taking advantage of how stabilized these instruments are now, we can use every calibration image we've ever taken to form information about where we expect calibration images to show up. And this will help us patch information that's missing and also denoise the information that we do have. So as a review, in classical wavelength calibration, when you try to interpolate with respect to pixel, you would use a polynomial. But here we can use a p-chip interpolator, which is a pretty basic cubic spline, but it enforces monotonicity instead, which helps with some deviations in the wavelength solution. And when you interpolate with respect to time, we used to use a polynomial, but now we can use principal component analysis to instead use all of the calibration images to identify the largest variations in the spectrograph, and use those to construct denoise and patched line positions. So as a test of the interpolation step, I show here that like the residuals to a single exposure. So here's just shown all the LFC lines, like a zoom in of what I was showing before. The x-axis is still pixel and the y-axis is shell order. And in color, you have the residuals. And so what I did is I took all the odd lines from this exposure and I used them to fit a polynomial and evaluated that polynomial at the even lines. And then I used the even lines and predicted wavelengths for the odd lines as a comparison of how well it can do. And you can see the residuals have all these like stripy structure in them. There are these patches, some like vertical diagonal streaks. But if instead of a polynomial, you use a much more flexible interpolation, you get these residuals instead. No more coherent structure, much lower values all around, and just does a much better job. And this shows that the denser line sources we have allow us the freedom to move from a parametric model, like a polynomial, to a non-parametric model, like a p-chip interpolation. And this flexibility, though well constrained by the density of the LFC lines, allows for the flexibility needed to account for all of these high order features here that we think trace back to slight non-uniformities in the optical elements in the spectrograph. And so by incorporating this, we can actually correct for those inadequacies, I guess you could say, in the hardware in our wavelength solution. And then when you put it all together and run a test also of the hierarchical step and how well it can predict known wavelengths, you can see that with the polynomial, here are the residuals on a line-by-line basis, which is why they're kind of large in meter per second. If you use a polynomial-based wavelength solution, if you just use the interpolation step, you get the yellow histogram. But if you also use denoise line positions, you get the black histogram, which has the lowest spread in RMS. This is all rolled into our much longer flat relative optimal extraction pipeline. And so we found that with our pipeline, if you're looking at a star on sky with a signal to noise ratio of 250, then you get a single measurement precision of about 30 centimeters per second, which is pretty good. So that's it for the data pipeline. For the data modeling, we've also been trying to move to a more empirical thing. So trying like the kind of like theme is letting our data tell us what we need to know. And so for this, we've started using wobble, which is a data-driven model for extracting RVs, but you can also use it to infer the underlying spectral components. So the framework of this model is that you have your observed spectrum, y sub n, and your observed spectrum is made out of a stellar component and a telluric component, plus some noise from your instrument. The stellar component is just this one stellar spectrum. So what the star is telling you, shifted by some RV shifts, indicated here by the P of V sub n obs. The telluric component, on the other hand, is a separate telluric spectral template. So what the atmosphere looks like from your telescope. It has these basis weights to scale it based off of how much atmosphere you're looking through, for example, what the makeup is, how much water is in the air. And then it's scaled by air mass also to take into account how much atmosphere you're looking through. And so the power of this comes from being able to actually separate out these spectral components. So here I have data 55 Cancri in black. The stellar model returned by wobble is in blue. And the telluric template is in orange. And in green is selenite, which is another way of gauging the telluric component. And you can see that even lines that are on top of each other are successfully separated out into stellar and telluric components with wobble because of the different ways that they behave. And this allows you to get RVs from the stellar template being shifted that aren't impacted by telluric lines and can also be extended, which is a project I'm currently working on, into separating it out into other components, such as stellar activity components, for example. And so the end result is a model that tells you all the different components in your spectral observation. And you can recover RVs from just the spectral component, the part that you care about, the part that's being impacted by the planets we're trying to find. And so when we use wobble, you can see here I'm comparing data from 3651. So the Keck data had an RMS of 3.4 meters per second, but the EXPRES data has an RMS of 0.417 meters per second, which is comfortably sub-meter per second, which was the previous kind of like standard of what spectrographs were able to deliver. And so just as a last note, currently the largest thing that haunts everyone in EPRVs is the idea of stellar signals. So the activity giving rise to photospheric velocities that would be mistaken for a bulk shift of the star being moved by a planet. And so I'm currently running what we're calling the EXPRES Stellar Signals project. And the idea of this project is that we're providing all of these EXPRES data sets to a number of teams, but it's really open to the entire community. And we have this timeline set up that will allow everyone to test the methods they have for dealing with this problem on EXPRES high fidelity data indicative of this next generation of spectrographs coming online. We'll have a series of check-ins because we also want to allow people to talk to each other, create collaborations that may make each method better and learn about what everyone's doing. And by early next year, we hope to submit a report that describes all the methods that people are currently trying, kind of the state of the field, what we're capable of doing, and provide some guidance on where we should move towards if we want to really figure out this issue. So in summary, for instrument stability, I've shown that our instrument is stable to within 4 to 7 centimeters per second. And the instrument performance has gone into in much greater detail in a Blackman 2020 paper, if you're interested. For the data pipeline, we have a single measurement precision of 30 centimeters per second on Sky, where the pipeline is described in much greater detail in Petersburg 2020, and a paper describing Excalibur and different tests we ran on it is currently in review. And for data modeling, we have a 41.7 centimeters per second RMS fit to a known planet system. And we also have an interesting result by Jens Hoji makers of a high resolution atmosphere detection. The 3651 results are presented in Brewer 2020, along with a description of our survey. And we have a few other planet papers in prep and in review. So that's my whirlwind tour of EXPRES. If there are any questions, I'd be happy to take them. And thank you all for listening.
Great, thanks for that talk. Does anyone have any questions? Oh, great, lots of questions. Nelson?
Yeah, just a quick question. It looked like the laser cone did not cover all the wavelengths, neither the blue nor the very red. If that's correct, how do you fold in the information from the two different ways of reducing the data?
Yeah, that's a good spot. We actually made a conscious decision to move the laser frequency cone redder because the redder wavelengths have less impact on the hardware of the LFC that needs to be replaced, and it's very expensive. And so we folded the thorium-argon information for where we don't have LFC data, but unfortunately with just the thorium-argon, you can't really use Excalibur. So for those wavelengths, we do just use the polynomial fitting method, but the polynomial is informed by both the LFC lines and the thorium-argon lines and has weighting with the error of the line associated with it.
Thank you.
David?
Nice talk. Can you comment a little on the expected, you said you got 30 centimeters per second RVs per exposure. How does that compare to what you would theoretically expect given the photon noise and number of lines and all of that? Is it in good agreement?
Yeah, so as you can see here, the single measurement precision does trail exponentially as we would expect with higher SNR. And I should mention that the single measurement precision is an analytical error. And so it traces pretty much what we'd expect because we were very careful about propagating our errors throughout the entire extraction process, which is perhaps why the RMS to a planet fit is slightly more indicative of the actual error, which is 41.7 centimeters per second. So it's close to what we would expect analytically. But of course, then we also have to roll in errors that we don't really understand. So how active the star is, which we don't have a good measure of, or if there are any other planets hiding in there that we're calling noise right now. Does that answer your question?
Yeah, thanks.
Okay.
Anna?
Hi, Lily. That was great. Thanks. Just to follow up along these lines, so you mentioned that kind of coveted precision was 10 centimeters per second. So it looks like you're getting there, but there's still a little bit of a way to go. So just wondering what are the next steps?
Yeah, that's a great question. I think right now the next step that everyone is thinking about is a problem of stellar noise. So like I said, the star is supposed to be pretty quiet, but there's still a jump right from the single measurement precision to the RMS that we're getting. And so we really want to understand better the different contributions of error to our data. We're pretty sure the instrument is stable enough. The data pipeline is already a large improvement from what we had before. But now that we've kind of like made the instrument noise and the noise from the extraction a lot smaller, what happens is that the noise from the star itself, those photospheric velocities, those become our largest error term. And with that perspective, they become much clearer and much easier to sort out. And so it's kind of like, Deborah loves this metaphor of when you're like nailing down terms of your error propagation. She likes to think of them as actual nails. And so we've nailed the instrument one down, we've nailed the data pipeline one down, and now the stellar one is sticking right up. So when we can nail that one down much easier, and once we nail that down, we'll be in a whole new regime, right? Where we might have to start over and figure out everything in this new regime with like 30 centimeters per second precision or 10 centimeters second precision. But right now, stellar noise is the one that we're all really looking towards to try and cement.
Great, thank you.
Great, well, we are right on time, so let's thank our speakers again. And thank you for everyone attending. And good luck with the rest of the week. Same old, same old. Bye, guys.